Okay. Welcome everyone to the third lecture of the mini school on a hands-on introduction to quantum computing with PennyLane. The mini school is presented by Omid, who's a PhD student in the quantum research group at Stellenbosch University, and his focus is quantum biology. So as always, please remember you can use the Q&A to ask questions, or at the end of today's lecture, you can raise your hand and I'll give you the opportunity to unmute yourself. So over to you, Omid.
Okay, thank you so much for the introduction. Okay, just I want online attendees to give me a thumbs up if everything is fine. You can see my screen and hear my voice. Thank you so much. Okay. So this is the third and the last lecture of this mini school series. And then if you want to have access to the previous lecture, you can first of all open this Google Colab. But how you can open this Google Colab, it's in my GitHub. Then I'm going to share it like the previous sessions. First of all, if you just check the chat to everyone, okay, you can open this GitHub page, and then in the GitHub page there is a Jupyter notebook. That everything is there, all the resources, all the codes that I use, everything is only one single Jupyter notebook. So I assume that everyone has access to this Jupyter notebook. And by this, if you open the first cell, there are some bunch of resources here. The number 6 is my playlist of this mini school series that you can click and then open here. Of course, it's lecture 1 and lecture 2, and then probably by tomorrow you will have the lecture 3 recording version as well. Okay, last session we talked about quantum teleportation, which is one of the most important quantum protocol in quantum computing. And today I'm going to continue as a follow-up. I'm going to talk about something which is called entanglement swapping, or teleportation of entanglement, which is also very interesting as well. But before that, let me just a little talk about different visualization tools that we have. Usually, people in the first lecture at quantum computing mentioned something about block sphere. I didn't mention, but now I wanted to mention. I wanted to basically find a way that use block sphere in PennyLane, but I couldn't. So apparently PennyLane doesn't have any built-in block sphere function or module. But let me open this. Not this one. Yeah, if you open this quantum computing resources syllabus mind map. Sorry, this closed distraction. If you open this, which I opened already here, there are a bunch of resources. Then you can investigate, you can explore. One of the resources is quantum animation interactive visualization tools and game, that I don't have time to talk about this quantum game, but about quantum visualization tools that we have, I want to talk about some of them. So you have access to this in the link that I provided in the Jupyter notebook. So, but before jump to this one, there is one single section here about block sphere, but because we cannot see the block sphere here, I'm going to use those tools. Okay, let's just quickly review this part, which is from a different angle. So here we have the concept. I provided this link also, I think, in the resources. Yeah, resources for this mini school. I added this block sphere, but as I mentioned, this is not enough. So here, let me talk a few minutes about blockosphere. In the first session, I mentioned that if you have a quantum state, if you have psi, you can represent it with alpha 0 plus beta 1. And alpha and beta are complex amplitude, complex numbers in general. But this is another representation. Okay. There's something in chat. I don't know if it's a question or your voice sound doubled. I'm not sure. Maybe we can.
Well, that's fine.
Okay.
I'm muted.
Okay, you are muted as well. Okay. Okay, somebody says it's fine on my laptop, so probably it's your problem because we muted everything except my mic. So anyway, if something happened, just let me know in the chat, and then Kishan will help me to coordinate. So, but this is another representation. So you have A0 plus BE to the I phi 1. This is another representation, and it's useful when we want to visualize our qubit. But remember here, A and B are real numbers. And A squared plus B squared is 1 according to the probability rule, because your state either is 0 or 1. So instead of A and B and this is the imaginary part, E to the I phi. Okay. Instead of A and B, you can use we need something to fulfill this identity. A squared plus B squared is equal to 1. So we can consider, based on the basic trigonometric relation, we can consider A is cosine theta over 2 and B sine theta over 2. So if you just plug this here, can you see my mouse? Yeah. If you plug just this here, then you can see this is, you can see, you can fulfill this identity. So instead of this, we're going to use this cosine theta over 2, 0 plus sine theta over 2, e to the I phi 1. This is another representation instead of alpha 0 plus beta 1. Here, we have two parameters, theta and phi. And that's enough for us to represent our qubit in a surface of blockosphere. Yeah, there is one caveat here. If you have a pure state, you can represent your qubit or the quantum state on the blockosphere surface. But if you have something which is called mixed state, I haven't talked about this, but if it's mixed state, it is inside the blockosphere. It's not exactly on the surface. We don't have a lot of time to talk about what is the difference between pure state, mixed state, but just keep in mind that this representation is specifically related to the pure state. So let me just zoom out. So this is your psi. This is X, Y, Z, and that's the representation that we can have in the blockosphere. So we have 6 important states here, or bases. 0, 1, which is the eigen state of the Z. We have plus, minus, which is the eigen state of X, and which we have plus Y and minus Y, which is the eigen state of Y. Or eigenvector or eigenstate, both of them are, you can use it interchangeably. So we have 3 different rotations, Rx, Ry, and Rz. So you, based on these pictures, you can see that Rx means the rotation around the x-axis, Ry means the rotation around the y-axis, and the Rz rotation around the z-axis. And we're gonna see this in action in a very animated form in a couple of minutes. Okay, let's assume some specific example. Let's consider, okay, all the usually quantum computer qubits are initialized in the 0 state by default. And then if you apply Hadamard to this, your qubit now in the state plus. So 0, you apply Hadamard, and then your state is in state plus. But now we want to see what is the effect of Pauli Z, or we can show that Pauli Z is exactly equivalent to rotation around the z-axis if you consider pi as a parameter. So 180 degrees rotation around the z-axis means exactly Pauli z. So here it's your state, the black arrow, and then if you apply z-axis, or rotation 180 degree around the z-axis, your state is now on the minus side. So this is the application, for example. It's again a nice visual representation. So, but these T and S also, I showed you in the first session in the table, these are also common gates, the common single qubit gates in the quantum computing, which is actually we can basically write them in terms of the Z rotation. So I mentioned we have rotation around Z. If we specify pi, this is exactly Pauli Z, which is Z. What about S? If instead of pi, I have pi over 2, which is 90 degree, okay? So instead of this coming to the minus side, this plus goes to the plus y. 90 degree rotation around the z-axis. And also for t, you see the t is something between plus and y plus. And t is actually, turns out that t is rotation around the z-axis if you consider your rotation angle pi over 4. So these are very interesting visual representation. There are some nice exercise here, but this is not about the 3D representation. I'm gonna quickly check. So there are some, I think, exercise here to just verify that I mentioned if you specify pi as a angle, these rotation around the z-axis is exactly equivalent to the z. And also you can do it for the, if you specify pi for rotation around the x-axis, it is exactly equivalent to Pauli x, and for the y as well. Ry, the theta is pi, if you consider theta is pi, is exactly equivalent to Pauli y. And there are some nice relation between y and x and z. And one important thing here is, although we can represent our Rx and Ry something like these metrics, okay, there are other type of representation. So we can represent Rx, Ry, and Rz can be represented as follows. So this is very important. Maybe some of you hasn't seen this, because this is, which is, we call it matrix exponentiation. So these x, y, z is not just a number. So e to the power of matrix. So why it's important? Because after you learn the basic concept in quantum computing, if you go to the more advanced topic, actually we had, I think here we had one specific school related to, here, an introduction to quantum simulation of closed and open quantum system. I put the playlist, it was 4 or 5 lecture here for quantum simulation. For this one, you need to sometimes use matrix exponentiation to calculate your Hamiltonian simulation. So this is important. I don't want to talk about this a lot, but just keep in mind that sometimes you need to exponent a matrix, e to the power of matrix. And then there are some nice, you can just check, this is matrix exponentiation. Here there are different methods. You see it's a very long Wikipedia. You need to spend a lot of time to learn, but this is very important when it comes to simulating quantum system. Okay. yeah, there are some solutions here. Okay, I don't want to talk about this today. And in this exercise, unfortunately, we can only see the, I think I solved this before the class. Yeah. And I highly encourage you to check this interactive codebook, because you can learn on the right side and then you can apply what you have learned as a code on the left-hand side. So this is, yeah, the title is plotting Rx, but when you're applying Rx to the state, what will happen? Actually, this is amplitude, and based on the theta that you have, I think it goes from 0 to probably 2 pi or something. And then you can check that if you apply this rotation, what will happen for the imaginary and the real part of the amplitude of the 0 and 1. Okay, that's good, but that's not what I wanted to show you. What I wanted to show you is if you come here and there are a bunch of blogosphere animation that people already created, and it's free to use, so why not? So let me just open one of this. No, I didn't want to. Let me just open like, okay, open like this. Okay, if you open this one, for example, okay, that's much better. For example, here you can, I don't want to check every detail that we have here, just want to show you the brief explanation, and then you have the link, and then you can check everything. Okay, our qubit is in the state 0. If you, for example, apply H, it goes to the plus state. And when here, for example, you apply Z, it goes to the minus state. Okay, and again, if you apply H, I show you that if you apply S, it's gonna be in the Y state probably. Okay, and then we have S dagger here as well. So remember, the gate that we use in quantum computing are unitary operator. And unitary operator means the inverse of an operator is exactly equal to the dagger. So here, this dagger, which means conjugate transpose of a matrix, is exactly equivalent to the inverse. That's why when I apply T, for example, here, and then T dagger, it goes back to the initial state. So, and also you have some nice visualization here about different rotation. You can check what will happen if you apply the different rotation like this, or for example, different rotation like this, and then also probability. This is very nice, and but we have other block representation as well. For example, here, what I mentioned, you can consider this as a psi representation. And there is a step-by-step explanation as well, the theta, and then phi. Let me see, what else do we have here? Oh, no. Let me open all of them and then quickly mention why there are, all of them have some feature. For example, here, I mentioned something about you can represent pure state on the surface, but what about the mixed state? Mixed state is something different from the pure state. So in the mixed state, you need to use something which is called density matrix. It's not about the vector, it's about the matrix. And with this blogosphere, when you learn the theory, you can come here and play around with different noise types. So noise also is always there. So depolarization, dephasing, amplitude damping, and different type of noise. You have the formula here, and then you can play around. But first of all, you need to learn about noisy quantum state and the mixed state. There is, I think, if I go to this course here, I think there is one specific course here, noisy quantum theory. And then if you go to the noisy quantum theory, yeah, you have all this explanation here, pure state versus mixed state. What is the meaning of density matrix, which is very informative. And then you can learn about this and then come to that check the website and then play around with this nice visualization tool. Then can play around with this different noise models. Here, there's another one, then with a little more detail, and yeah, there you have lots of things here. And then this is also one animated part that you can see the effect of Hadamard, for example, on different states. Yeah, I think that's enough for this part. But also from this, this is not PennyLane. If you check this mind map again, and then you can find another nice tool, which you don't, it's just a drag and drop, which is called Quirk. I found it very useful. If you don't even want to code one single line, okay, I encourage you to do that. But if you don't want to do that, you can just open this website. Okay, check this website. Welcome to the Quirk. Okay, there are some tutorial here, but again, I don't have enough time to go through those tutorials, and also some predefined builds, like a circuit. If you click on each of them, you can see the circuit. It's like a big circuit, and you can just see the results. But if we just click here, then you will see, okay, this is initialized in 0. You have a bunch of things here. You have block sphere, you have the density matrix, and then you have chance of seeing 0 or 1. Yeah, basically off means 0 and the on means 1. If, for example, the qubit is in 0, and then if I apply Pauli X, now is on, then you can see the 100% is 0. And then if I apply, for example, a Hadamard gate here, 50% on, 50% off. Also, you can see the effect of immediately in the block sphere as well. What is this one? This is the amplitude of, for example, 0, 0, and this is the amplitude of 0, 1. So you can get a lot of good information at the beginning. If you just want to quickly check something, you can get a lot of useful information from this part as well. I don't know how many qubit can you have to simulate. I think maybe around 20 or something like that. But that is also very useful. You can check the measurement. I haven't checked the measurement. Yeah. But you can check all of this different gate. I think in some point you can make your gate as well. So, by the way, the link is there, and then you can check the tutorial and learn a lot of things about this amplitude, the blockosphere density matrix chance. Okay. And this is the noisy quantum computing. I'm just going to close it, close this one, and also close this one. Okay, back to our story here. Okay, I already talked about these. These are for the previous sessions. One thing that I didn't mention, I should have mentioned it before talking about GHZ, because I mentioned about something about GHZ, but I didn't mention about Bella state. Where is that Bella state? Yeah. I just added this one here, the famous Bella state. If you want to just quickly check, we have 4 different Bella states, which are basically here. Again, psi plus, psi minus, phi plus, and phi minus, and then I think, yeah, I think I put it here for you. Okay, so this is the answer of at a specific coder size 1.14.1 or I.14.1. Then you can create all these Bella state and then print them. Okay, so you have psi plus, psi minus, phi plus, and phi minus. All of them has this part, Hadamard CNOT, but for this one, we don't have anything else after CNOT, but here we have Pauli Z, here we have after CNOT Pauli X, and here we have both. Then you can create this. This is a very nice exercise to do it with pen and paper as well. So just okay. Well, that was about the Bell state. Don't forget to check and drive all these 4 states. Okay, usually, yeah, I should have told you about Bell state before GH state, because GH state is also similar to Bell state. It is maximally entangled state, but for 3 qubits. But Bell state also is maximally entangled state, but for 2 qubits. Okay, and the last session also I talked about 3 different measurements that we had: probability, count, and the sample. I'm going to talk about the force measurement that we have. Okay, we have other measurement as well. These 4 are very important, which is called eigen value, expectation value of an eigenvalue. Expectation value, yeah. Where's that? Okay, but before that, let me just quickly mention something about subcircuit that I didn't mention last session. Sometimes what I show you here, for example, first of all, the quantum circuit, first of all, in PennyLane should be Python function. Okay, this is the standard Python. If you start working with Python, this is something like very standard. You can define your function name and then applying some other function and then return something. This something can be your state, can be the probability, can be the count. Okay, could be anything or sample. But sometimes we don't want to return anything. We just want to create a circuit, but just keep it as a sub-circuit and then use it later. Okay, how can you do that? The only things that you need to do is quantum function that do not return anything can be used as a sub-circuits, smaller pieces that build up to a larger circuit. So here, for example, this is a very simple example just to give you the general idea. Okay, here I have a sub-circuit, and also actually it's a parametric sub-circuit. I apply Rx to the qubit 0, I apply but I need to specify angle, so that's why I have angle. So when I want to use the sub-circuit, I need to specify this. Pauli-White doesn't need any parameter, and also this is CZ, which is the control Z. You need 2 qubits, 0 and 1. Okay, and as you can see here, there is no return. Okay, no return means this is a sub-circuit that you can use as a sub-circuit 1. Sub-circuit 2, this is just a random circuit. I don't care about this specific what this circuit do, but I just wanted to show you that this is another circuit. And then we can put built up to a larger circuit. Okay. Okay. Here, my full circle, as you can see, there is theta and phi as well. So the phi is another parameter for that sub-circuit 1. So what I did here, sub-circuit 1, I put just barrier here to just separate different part of the circuit. In the sub-circuit 2, again, another barrier, and sub-circuit 1 again. So basically what we did, sub-circuit 1, sub-circuit 2, and sub-circuit 3, 2 again, 1 again, and then combine all these 3 sub-circuit. And then you can just check what is your full circle. I recommend you to use PennyLane style, and the theta and phi. I define theta and phi here. This is based on radian. Okay, it's not degrees. Keep in mind. And then you can see this is your sub-circuit number 1, this is your sub-circuit number 2, and this is your sub-circuit number 1 again. Okay. And one important thing is when you write a paper in, for example, quantum computing and quantum algorithm, usually people want to check if their circuit is efficient or not. There is a built-in function in PennyLane, which is called QML specs. Then if you put this QML specs, you can get a lot of information about your circuit. So I just define another variable specs underline func and QML specs. I use my full circle, which I define here. Okay. Again, I put this as a parameter, and if you just run this circuit, you get a lot of information. Number of wires, of course, is number of qubits. Number of gates, 11 gates, apparently 1, 2, 3, 4, 5, 6, 7, 8. Probably they consider, I think, barrier as a gate as well. I need to check it again. And also what type of gates you use. Usually, when you publish something, you need to specify specifically 2-qubit gate like C0. You need to say, okay, my algorithm is more efficient because I use 10 C0 instead of, I don't know, 20 C0. I use 1 CZ instead of 3 CZ. So that is something that you can quickly check with QML specs. Also another feature of another aspects of your circuit, which is very important also, is depth. Here, the number of parallel quantum operation that you can perform, and here is 9. Again, I think that consider this barrier as a 1. If I'm not mistaken, 1, 2, 3, 5, 6, 7, 8. Yeah. So if you want to get your exact depth, it's better to not use this barrier. Anyway, that's also something interesting and important. Another things also is control unitaries that you need to learn. What does it mean, control unitary? Sometimes you have some specific function like this one, which is CZ, or this one, which is C0. Okay, you have this. Or I didn't mention, but with Toffoli gate also you have CC0. And this is swap gate. So these are 2-qubit gates, which is controlled. But sometimes you need to have more freedom to basically control your qubits. Here, you need to either use QML control if the gate exists, or you can use QML controlled qubit unitary if you want to have a custom matrix to define this kind of control unitary function. Okay, what happened here? Okay, usually you need to define your device or simulator and then decorator to basically add your function to the quantum device. And okay, this is just a simple Hadamard. The point is here. Here, I'm going to apply Rx. Of course, I need to specify angle. My control qubit is 0. My control value also is 1, which means if it's 1, you should apply Rx. The circuit will apply Rx. And the wire number 1 is my target. And I also change it a little bit. So if we change the control qubit from 0 to 1, and you will see what will happen. And also control value can be 1, can be 0 as well. I changed this part as well. So what's the difference? First of all, here you can check the state of the qubit here. This is not a point here, but just to show you how to use this. So this is the single Hadamard that I put at the beginning. This is what we can do. Okay, this is your control qubit, is your target qubit. And in the second part, I changed the target and control. And also, I changed the control value. Here should be 0. In PennyLane, and if we use PennyLane style for the drawing the circuit. This pink means that your control value can be 0 as well. Okay, so your control value can be 0. If it is a 0, if the control value is 0 on the qubit number 1, it applies Rx to the qubit 0. Okay. But what if I have a custom matrix? If I have a custom matrix like this is a custom, of course, it should be unitary. You can check it later. But I want to apply this custom matrix like a control gate. Okay. I think I show you qubit unitary if you just want, you don't want to define control, but you just want to define a matrix as a gate. You can use qubit unitary. And but here you need to use control qubit unitary. So I define U, it's just a normal unitary matrix. And again, okay, I think I define it here again. I just wanted to show you what is U. And here I just apply hot number to the qubit number 1. I have 4 qubit. And then control qubit unitary, which is U, is my operator. And these are the wires 0, 1, 3, 2. And you will see it was 0, 1, 2, 3 by default, but I changed 2 and 3 to just show you something. And also the control value is 1, 0, 1. Again, for 1, 0, 1, you can see this is 1, this is also 1, this is 0. So if this circuit wants to apply this U to the qubit number 2, when the qubit 0 is 1, qubit 1 is 0, and qubit 3 is 1, it applies this U to this qubit number 2. So and that's why I actually change this 0, 1, 3, 2. When you say 0, 1, 3, 2, it's like 0 or 1, 3, 2. So the last one basically is the last argument here is your target, and then the rest is the control. And this is the control value. Okay. These are very nice tools that you have in PennyLane that you can use. Okay, let me just. Okay, I remember last session, one of the questions at the end of the session was, okay, we managed to show how can we teleport a quantum state from Alice to Bob with either classical communication, pick up the phone and tell Bob what to do, apply Z or apply X, apply both Z and X, or do nothing, or we did defer. Okay, here was the classical standard quantum teleportation, and here was like, I think, deferred measurement. So here we don't need classical communication, but but these source and also Alice qubit needs to be close to the Bob qubit. Okay, but by the way, the point was to basically here teleport this qubit by measuring it. By measuring it means that destroy this qubit here because it will collapse to something 0 or 1, and then create this qubit here in the Bob part. Okay. But one question was actually, what's the application of this? And I didn't mention, I skipped this part, but I shouldn't skip this part actually. The problem was no cloning theorem. So if you have a unknown quantum state based on the no cloning theorem, that you can just quickly check and prove that you cannot copy an unknown quantum state, arbitrary unknown quantum state. So because you cannot copy, So quantum teleportation is one of the methods that gives you this ability to teleport a quantum state. So it's not possible to copy this, but okay, I can destroy my qubit and create that specific qubit, exactly the same qubit, somewhere else. So keep in mind this no cloning theorem is very important. Then you can check, this is the same tutorial, okay? You can check the how to prove it, because it's very easy to prove this, okay? That was one reason that I wanted to mention. Let me check. What else should I tell you? Okay, two things. Okay, one thing is the measurement of the expectation value on observable, and the other thing is the gate teleportation. But first of all, let me just skip this and talk about gate teleport. Sorry, not gate teleportation. This is something a little more advanced. Entanglement swapping or entanglement teleportation. That is also very interesting phenomenon. We have 3 people here: Alice, Bob, and Charlie. And Alice has 2 qubits. Okay, so here A1 and A2 belong to Alice. So Alice has 2 qubits. This is Bob and this is Charlie. So what we want to do here is basically, first of all, AY, or the qubit number 1 of Alice, is entangled with the Bob qubit. And also, qubit number 2 of Alice is also entangled to Charlie. You can see there is no entanglement between Bob and Charlie. And the point here is we want to swap the entanglement from Alice to Bob, Alice to Charlie, to Bob and Charlie. So they have, and they don't have any interaction. That is very interesting. Okay, let me just go step by step what we did here. So first of all, we have 4 qubits: Alice number 1, Alice number 2, Bob, and Charlie. Okay, here we just define our standard device, and this is just a simple function to define bell pair. Okay, I just wanted to quickly create this famous bell state. What is next? Here, so instead of every time using Hadamard, CNOT, Hadamard, I just use this bell pair. This is something easy. So with this 2 line, I created an entangled state between Alice qubit number 1 and Bob, and Alice qubit number 2 and Charlie. So still there isn't anything between Bob and Charlie. And here, Alice perform a CNOT Hadamard measurement. Sometimes we call it, it is very similar to teleportation. I will show you the 2 circuits close to each other. So, and then, so Alice created an entangle with Bob, Alice created another entangled pair with Charlie, and then Alice applied CNOT and Hadamard to her qubits, not to other qubits. And here, it's very, again, similar to quantum teleportation. Alice start to measure. So let me show you here, maybe it's better. So entanglement between Alice and Bob, entanglement between Alice and Charlie, and here, this only happened between Alice. So nothing between Bob and Charlie, or Bob and Charlie and Alice. So only Alice qubit 1 and Alice qubit 2. And then Alice start to measure her qubit here. So 1 and number 4 here is the Alice. So, and this is exactly similar to teleportation. When Alice measure her qubit here, okay, she can pick up the phone and call, I think the third one, yeah, call Charlie. If this is 1, you can apply Z, and if this also is 1, you can apply X. If 0, 0, Charlie doesn't need to do anything, and if it's 1, 0, either he needs to apply Z or X. So this part is very similar to quantum teleportation. We need classical communication again, but the point here is what we get after that. Okay, let me just quickly go through this. So all is measured, and this is the conditional measurement. Okay, Alice sends the 2 classical bit is a 0 or 1 to Charlie, and Charlie applies the usual teleportation correction on his qubit. Still no communication or no interaction between Bob and Charlie. After the correction, Bob and Charlie qubits are entangled. That's the magic. That's where the magic happened. Okay. Now we want to basically verify this. Okay, how can we verify that Bob and Charlie qubits are entangled? Okay. First of all, because this is maximally mixed state, and we want a part of the circuit, instead of state, I use density measures. I think I mentioned this last session as well. So sometimes you need to return density matrix instead of vector. And wire B and C, which means, so this is a density matrix specifically for Bob and Charlie. Okay, and that's the visualization. And then you can compare this with the teleportation after class, after the session. These are very similar. You know, this specifically the last part is very similar. Okay, how can we check? This is rho or density matrix of the joint Bob and Charlie. If you want to see a better version of this, you can use the SymPy package to just show you exactly this matrix. So 0 0.5, 0 0.5, 0 0.5, 0 0.5, and the rest of the elements are 0. Okay, but we basically claim that this is entangled state. Okay, how can we basically verify? I just checked here. If I just created, this is another, this is not related to the entanglement swapping. I just use A and B to just show you if I create an entangled qubit. Okay, it's not related to the entanglement swapping. And if I just apply these gates, and then I want to show you that this is exactly what we get here. Okay, maybe you can say this is just a vector, but I showed you the matrix. Okay, no worries. We can, it's fine. It's still, you can get the density matrix as a return of your function. So if you check this, you will see that this is exactly, we connect. This is exactly the density matrix of the joint Bob and Charlie state. So maybe I can add something here to just separate it. This is not related to the above. I just created standard maximally mixed state. Okay. Again, you can, I just try to explain and expand this part. If you have something like the previous code, instead of QML density matrix, you can have QML state. Okay, and if you have QML state, this is another method. So if you have QML state, you have this instead of the density matrix. So you can have the same, basically, you can have the same circuit, and your return sometimes can be, it depends what you need, or it depends what you can. Sometimes you cannot have a state as a return. So here, this is the vector and this is the matrix, but there is a method in PennyLane that you can use to create this vector to the matrix. So which again, you see that this is exactly the same as what we have here, which is a maximally mixed, maximally entangled state between Bob and Charlie. Yeah, you can use NumPy also to do that for you, but okay, you have the freedom. I don't have a lot of time, but you can check this defer measurement approach in entanglement swapping, because I mentioned in the quantum teleportation, also you can do the measurement at the end. Here, I think you can do this at the end as well. So, but the point here is instead of Alice calling to Charlie to do this or that, they need quantum interaction here. So C0 and CZ interaction between Alice and Charlie. Okay, two different methods. Still Bob and Charlie don't have any interaction. Okay, almost finished the session, except just need to quickly mention something about expectation value and then finish the session. Because we don't have time, but just keep in mind in a lot of problems, we don't just want to count or sample the data, or I don't know, but we have probability. Sometimes we need to specifically calculate the Hermitian matrix, which is observable. We want to see what is the result if we do this experiment. So if you basically have an observable in physics and you measure it in the lab or in your code or whatever, what you get, we call it eigenvalue. For example, we have here the Z Pauli Z operator, okay? When you measure it in the experiment, either you get 1 or you get -1, okay? That's fine. So, but what is the meaning of expectation value here? Expectation value, most of the time, it's not either 1 or -1, because these are eigenvalue. This is the results that you get in the lab or in your code. But expectation value is like a weighted average of what we would see over many experiments, okay? That's a very simple, for example, simple example here. The example here is 70% of obtaining eigenvalue 1, 30% chance we obtain the eigenvalue -1. What is the expectation value? So you can just check the expectation value is 0.4, which is not 1 and not -1. Okay, so your eigenvalue can be completely different from the expectation value. Just keep in mind. And then also there are some other examples, then you can just check those examples as well. But how can we, because I just wanted to keep time for Q&A, but how can we check this in, for example, PennyLane? One method is this. First of all, this is the cheat sheet. You have this QML.expectation value. Okay, this is the expectation value. And then you can use in the return part, I want to calculate the expectation value, for example, of the Pauli Z on the first qubit 0, or the first qubit 0. Okay, based on this circuit. So this is how we show this. So I think I just put a few example here. Yeah, for example, this is a circuit. I apply Rx with this parameter and the Hadamard and the Pauli Z. And now I am interested with this state, because if you just check the teleportation, what happened, but if you check the expectation value, okay, you can specify this is the expectation value I want to calculate, but based on which state. You see that this is psi, bra, and psi cats. So you need to specify your expectation value, but in which state? The state that circuit shows you which state. So this creates the state from 0 to something else. And then you can specify this Pauli y, which is, for example, minus 0.7. And then I just played around with some other circuit here. You can see the expectation value. Yeah. Probably I'm gonna leave this for you to play around. Yeah. Okay. Also, it's possible to specify you have a Hermitian observable. Your observable should be Hermitian, and Hermitian means if H is your matrix, it should be equal to H dagger. This is different from unitary, keep in mind. So you can define your A as a matrix and then put it here, Hermitian A here. Okay, so you need that specific code to use to calculate your expectation value of that custom matrix. Okay, and yeah, by this I'm gonna finish here and finish this mini school. Thank you very much, and let me just check if I have some. Maybe you can. I don't know if you want to ask your question. You can raise your hand, and Kishan can manage to unmute you, and then in the chat we have, is there a function for optimization of an algorithm, say use less gate if you have an arbitrary circuit? That's a very good question. Yeah, I think there is, at least on Qiskit, I know there is some optimization level, and they try to simplify this procedure with something which is called primitive. But in PennyLane, I haven't checked, but there should be. Probably I will check it after session, and if I find something, I will put it into this Google Colab. But thank you very much for the question. It's a very, very important question. And actually one of the goal of all these paper usually is to how can we optimize the algorithm by less gate. Okay, use the fewer gate, fewer 2 qubits gate, fewer CNOT, and also smaller depths. Thank you very much. Is there anything in Q&A? Because I don't have access to Q&A. There is not. Okay.
If you'd like to ask a question, please raise your hand and I can unmute you. Or you're welcome to type it in the Q&A or the chat.
Okay. Seems there, yeah. Thank you, Michelle.
Okay, so yeah, there seems to be no questions. So thank you very much, Omid.
Thank
It was
you.
a nice lecture. I enjoyed the examples, especially like visualizing on the block sphere.
Yeah, thank you so much. Yeah, all the participants will have this on the YouTube as well, probably tomorrow. And yeah, you can have access to this code, everything, and then feel free to send your question, I don't know, email or LinkedIn or somewhere. Okay.
Yeah. And as always, these recordings should be uploaded to the NITheCS YouTube channel.
Yeah.
Okay, thanks for joining,
Thank you,
everyone.
And bye. I think you need to.
So can I just end it now?
Yes, if you end.
Where does the recording?
Cloud.
Oh, okay, so I can just.
Yeah. So usually should be.
Yeah, I just said. Yeah,